Oh, and the other thing I have to do is I have to include a live transcript. This is a requirement by Berkeley, evidently, in order for it to be posted. Cool. All right. Yeah. So thank you all for joining us today. I believe this is now the sixth N3AS seminar of the semester. If that's the wrong number, then don't correct me. We are absolutely delighted to have Raffaella Margutti here to tell us about transients and multi-messenger astronomy. So Raffaella, whenever you're ready, we are very excited to hear your talk.
All right. Thank you for having me. So I just want to minimize myself, get rid of the cooling controls. Can you see my screen right now?
Yep. Yeah, it looks good.
Awesome. Okay. Yeah. So thank you for having me. So today I thought to give you a little bit of a tour of what we do in my team with a special focus on multi-messenger astronomy. And while we wait for LIGO to switch on in December 2022, or who knows, maybe a little bit later than that, I wanted to give you an update of what is still happening with the neutron star merger of 2017, which is still the only object for which we were able to find gravitational waves and light at the same time. So this is one slide of motivation about why I deeply love studying explosive transients, and the reasons go from all the way from cosmology, like the type 1a supernovae that allow us to measure distances in the universe, to the fact that when the stars explode, they release into the environment their chemical elements that they synthesized, but also at the same time they deposit kinetic energy in the environment, and they can drive very powerful outflows, like you see in that galaxy in the upper right corner. And of course, since we're here talking about multi-messenger, one of the reasons why I deeply care about these stars is because they can produce black hole and neutron stars, and sometimes they're born such that they can merge on the Hubble time, and so they can be sources of these gravitational waves that we can now detect. And hopefully in the future we will be able also to add neutrinos from the same sources as well. Also, I forgot to say, but if you want to ask questions, so it's totally fine, and actually welcome to ask me questions while I give the seminar online, and it helps me knowing that there are humans on the other side of the screen. So let me just spell out aloud what are the questions that I'm trying to address with my team. And you can see that we have two big question marks on either side of stellar explosions. We do not know which stars explode, and we do not know what they leave behind. And we do know that most of these massive stars, they actually live in binary systems, and some of them, they can actually stay together until the end. And they can merge using gravitational waves and light, and we would really much love to know what is left behind in that case. So if I were to just put down these questions, here they are. So what are the progenitors of these stellar explosions, and what do they do as they approach the final moments of their evolution? What powers these stellar explosions? What are the properties of the newborn black holes and neutron stars? And last but not least, how do these compact object mergers look in the EM spectrum, and what is left behind? So all of those are fairly big open questions that motivate my day-to-day research. And as in any field, the questions might be there for a long time, but why now is a good time to try to find a solution to these questions. And I want to give you a couple of arguments. One is very much related to a technological revolution. Here I put on this slide some of the major players, the time domain surveys, like ZTF, and I put there the Young Supernova Experiment, YSE, that I co-funded. And of course, looking at the future, there is maybe in a couple of years, the LSST survey on the Rubin Observatory. So those are the machines that are allowing us to take pictures of the night sky. So we can actually sample the fourth dimension for the first time. We can sample the time dimension in the universe in real time. And the beauty of this is that this is something that is happening not only in the optical, but also at radio wavelengths. In here, I'm emphasizing the SKA. hopefully, I say hopefully, we will also have something similar in the X-ray range, so wide field X-ray instrument that right now we are missing. The world of UV will enjoy ultrasat in a few years, so we will have a UV time domain machine, but yet the soft X-ray part of the world is lagging behind. So what have we been doing with these new facilities? So we could sample pieces of the parameter space of transients that we already knew. So here I'm plotting a supernova light curve. We were used to find those around the peak, fundamentally because the supernova community relied heavily on amateur astronomers, and they're humans, they tend to find things when they're bright. And right now, instead, we have the possibility to sample what happens before, so we can have access for the first time to what I call the rise time science and the pre-supernova outburst science. When I was a grad student, the theory that I was sold was that stars just sit quietly and wait in the last 1,000 years until the end comes and core collapse happens. Now, right now, we know that this is actually not true, and I would say that is way more reasonable, that stars sort of feel that something is really not right, that their fuel is over, and we know that they experience a number of outbursts. The origin of which is completely still debated, and we are still trying to understand what's going on right there. But at least now we know that that is happening. And just like any time we have new capabilities, not only we can sample portions of the parameter space of things we already know, but we can also find new things. And in that cartoon plot, I'm emphasizing two types of transients, the fast transients in red and the superluminous supernova-like transients in blue. And I would like to give you an intuitive understanding of why, in spite of this transients being extremely luminous, why we were not even aware of their existence until a few years ago. The reason is pretty simple, it has to do with timescales and where we were searching for this type of phenomena. So timescales, here's what I mean. We were used to do our monitoring just like those vertical dashed lines. And guess what? We would be missing the fast transients because they would just happen in the gaps of our monitoring. And we would also be missing the very slowly evolving transients for the fundamental reason that the way we go about finding new stuff in the sky is by looking for differences between the image before and image afterwards. And in this case, the difference, the dynamical range of the difference was not large enough for that new thing to actually become a trigger. So it was not enough for us to not be classified as noise. So right now we're doing our monitoring like that, so way faster cadence, so we can find these fast transients, but also we go back to the same part of the sky season after season. I like to remind the theorists that there is the sun, and so there are seasons if we want to do optical follow-up from the ground, and so it's important to go back to the same part of the sky season after season, and that allowed us to find the very slowly evolving but very luminous superluminous supernovae. The other half of the answer to the question has to do with where we were looking for this explosive phenomena. And as I said, we were relying heavily on amateur astronomers, which tend to like pretty galaxies. So they tend to take pictures of pretty galaxies like the spiral that I put in the lower left corner. But a galaxy like the smudge that I put next to it might not be a preferred target for our amateur astronomers, which meant that these dwarf galaxies were actually not targeted that heavily. And it just turns out that very peculiar transients, very peculiar explosive phenomena can happen preferentially in dwarf galaxies. And this is actually the case for both the fast transients and the superluminous supernova transients as well. So the second point that I want to make of why now is a good time and try to explore the open questions that I laid out is because of the multi-wavelength astrophysics. So we can study the sky across the spectrum And this multi-wavelength astrophysics is the very first step towards what is now reality, which is multi-messenger astrophysics. So combining information from different messengers. And point number one is giving us discovery power. And again, this is very much a technological, it's just related to the evolution of technology. And point number two, this follow-up across the spectrum is what my personal opinion is the only way to understand what physics is happening behind this transient. So it's the way to understand what we're looking at. So we have the combination right now of discovery power and understanding, and that's why I believe is a good time to try to approach the questions. So these are the questions that I laid out in the previous slide. And I want to give you a feeling about how we go about trying to answer to these questions on our day-to-day life. And in my team, the motto is no photon is left behind. So whenever we have a particular transient that is of interest, what we do is to trigger all the facilities that we can put our fingers on. We do have active proposals on, in this case, this was for the 18 cal transient. Those are the active proposals that we had for that particular transient. At any single point, the team has on average 30 programs approved, so that when we have something in the sky that satisfies our interest, we can just repoint all of these facilities. As you might guess, it's not that this spacecraft, radio antennae or telescopes are sitting there idle. So that means interrupting some of our colleagues. There are some social aspects of being a time domain astronomer that I would love, if you want to know more, I'd love to discuss maybe over dinner at some point. So how do we play this game? So the discovery engine, we have a discovery engine, and up until let's say 10 years ago, a discovery engine would just be some telescope, some survey, and that would be enough. Right now, this is no longer true, and the discovery engine is actually made of two big pieces. So one is still the time domain survey, and here I'm emphasizing YSC and ZTF. But this would be completely, not completely useless, but definitely not as useful without being coupled to AI efforts, where we basically have machine learning algorithms that really help us understanding what is important, what is noise, and what we are looking at. Did I see a raised hand or something for a question? Because I saw something happening on my screen.
I don't see any raised hands,
Okay.
but if somebody does have a question, then of course. Okay, it looks.
Okay. All right. So we have the discovery engine that has those two pieces, and whenever the telescope plus AI tells us, hey, you do have a transient or target that satisfies your interest, then this trigger goes to the follow-up team that starts understanding how to coordinate all of the spacecraft, radio antennae, and telescopes to look at the same part of the sky. All right, moving forward, here is how I like to think about what I believe are discovery frontiers in the world of time domain multi-messenger astrophysics. We have a diagram of luminosity on the y-axis and timescales on the x-axis. And T0 here is defined as the time when we have some explosion, or if we're talking about a neutron star merger, that would be the merger time. And I try to emphasize with color the places where I believe we will actually be very well positioned to make discoveries in the future. And I emphasize the pre-supernova, like all the pre-supernova life of the stellar progenitors. So I will not go into any detail in this talk, but I just want to let you know that I strongly believe that LSST will have a huge impact in that part of science. So if you care about that, LSST is going to be your favorite machine. And then there is the world of very fast timescales that is related to the talk today. There's the world of things that we call the fast transients. Those are the F dots in the plot. Those are things that vary on a time scale of days. In yellow, bright yellow, I colored the world of counterparts to gravitational wave sources, which is the focus of the rest of this talk. But I also wanted to emphasize the very late time evolution of normal supernovae that we know already. And that very late time evolution, both at radio wavelength, but also spectroscopically in the optical, whenever we will have the 30 meters telescope. So I believe that in the future, we actually have the possibility to make a lot of progress, both on the stellar progenitor side, but also on the subject of compact object formation. And today with you, I will focus on the EM counterparts to electromagnetic counterparts to gravitational wave sources, and specifically 170817. So I don't have to go into any details with this crowd about this event. This is just to remind ourselves that beautiful day of August 17th, 2017, where LIGO, Virgo, announced to the world there's a gravitational wave signal, followed very quickly after 1 second or so by a detection of gamma rays, which is the gamma rays were actually the first EM counterparts of this found for this event, to which followed a very dense follow-up across the spectrum. And what we were looking at with photons was the combination of a number of different of radiation from a number of different outflows. And here I sketched them with that cartoon. You do have a quasi-spherical component that this is the place that I'm sure you heard, that's where we form the heavy elements. That's where gold is produced as a kilonova part, with those two components, red kilonova and blue kilonova. But for us, it's okay to think about those as a spherical for now. And then we have a very aspherical component that has to do with ultra-relativistic jet. That by now, finally, then I believe the entire community now agrees with the fact that there was an ultra-relativistic jet. That jet was carrying a lot of energy, and it's around 10 to the 51 erg. It was extremely collimated, collimation of a few degrees, and we were not aligned with that jet, but we were something like 20 degree-ish off axis. And that jet was also surrounded by some mildly relativistic but wider angle outflow that in the literature of GRBs is usually referred to as a cocoon. So effectively, we have one outflow that dominated the early times in the optical and optical UV near infrared with a thermal, let's call it thermal component, and the non-thermal part that was always dominated by the ultra-relativistic jet and its cocoon. So if we just have a quick look at the counterpart of the optical, let's say the optical signature here, what you're looking at, there are selection of bands of kilonova, of the kilonova emission. You can see UV in purple, and then we go all the way to near infrared with KS band in red, and you can clearly appreciate how the evolution is much faster at bluer wavelength than the red wavelength. But in any case, we are still talking about something that evolved on very fast time scales of, let's say, a couple of weeks, and that's basically over. And I want to emphasize one thing, that the last spectrum for this kilonova was taken at 9 days. And after that, even 170817, which in the world of neutron star mergers was literally around the corner at 40 megaparsecs, even for this exceptionally close by event after 9 days, we lost the capabilities to take spectra from the ground, even with the biggest telescopes. So we are.
Raf, yeah. I'm sorry, can I interrupt just really quickly? We have a message in the chat here from David Brin. David, did you want to read your question aloud, or would you like for me to do it?
You go ahead.
Okay. So David has said, are you saying that blue and red kilonovas and the jets all happen in the same event, or are these seen in different events?
So here I'm talking about the same event. So yes, the red kilonova, the blue kilonova, the jet, and the cocoon, they are all identified components of 17-weight-17. Yes, all in this same event. It is very true that in a cosmological short gamma ray bursts, in many cases we just see the jet, but that's it's more of a sensitivity issue.
Thank you.
Awesome, yeah. And when I say red and blue, of course, it refers to the colors of the observed colors of this kilonova. And you can clearly see from this plot here that the blue component fades away very, very, very quickly. And the red component instead is alive for, let's say, 10 days or so. But in any case, from the perspective of those that do follow up of transients, this is something that is faint and is fast evolving. And the two ingredients are really, really making the game of finding these kilonova transients without any association to GWs or gamma rays extremely challenging. It's a tough game to play. And there is one thing that we know for sure, though, that the short gamma ray bursts are the cases. Let me go back here. The short gamma ray burst. Oops, I went on the opposite direction. The short gamma ray bursts are the cases where we are looking down along the jet axis, and those are events that we detect in the gamma rays, not through gravitational waves. And for some of these short gamma ray bursts, we tried very hard to find signatures of this kilonovae. And in this plot, which is a little bit complicated, but I'll tell you what is the take-home point from here. So in this plot, what I'm plotting are the luminosities of this potential kilonovae in other short gamma ray bursts compared to the kilonova in 17-weight-17. And that AT2017 GFO, that's the name of the kilonova using the IU standards. So just think about it as a kilonova 17-weight-17. The one thing that I want you to bring home from this plot is that even if finding kilonovae in short gamma ray bursts, they're typically a redshift 0.1. So 17-weight-17 was at 40 megaparsecs. Short GRBs are at 500 megaparsecs or even more distant. So even if it's extremely challenging to play that game with short GRBs, we can say already that there is a diversity of kilonova emission in short gamma ray bursts. And that's why the distribution, we can see in the distribution, we can already see kilonova that are potential kilonova that are fainter than 17-weight-17 and kilonova that are actually brighter than 17-weight-17. But again, what you're looking at is the plot after 20 years of follow-up of short gamma ray bursts, and we can still count on our fingers the kilonova, potential kilonova counterparts. That's why 17-weight-17 is such a beautiful case. If we have a look at the galaxy of where 17-weight-17 happened, here it is. It's an early type galaxy. You can see 17-weight-17 is that AT2017 GFO localized with the dashed blue circle. And here, the only thing I want to emphasize is that the distance that we're talking about, this 40 megaparsecs, is literally extremely close by for anybody that is trying to do short gamma ray burst studies and also gravitational wave follow-up. So how are we planning to play the game here at Berkeley about finding this kind of parts? So as I said, so LSST will be a major player in this game. However, within LSST, I'm leading the gravitational wave follow-up team. One of the challenges of LSST is that LSST was not built to do gravitational wave follow-up. And after how many years? It is now 7 years of trying to convincing the people in power to have a target of opportunity modes, which means the possibility to interrupt LSST. It seems that we are getting the green light, but in any case, LSST can only be used as a discovery machine. So LSST can be used to find the counterpart, but not to follow the evolution of the counterpart. So for this reason, and also to have a little bit of a better quality of data, we started here at Berkeley under PI-ship of Peter Nugent. A new time domain survey is the LaSilla-Schmidt Southern Survey. It's going to be a LaSilla, as the name suggests, in the southern skies. And we think in the, I would say, optimistic case, we should be in the sky in the second half of this year, probably more realistic around December 2022. But the key point here is that there is this new time domain machine that is coming online, and we will be able to complement LSST. So if you are interested in LSST data, you will have a lot more data to play with, because this data that we will be acquiring will be public immediately, more than 90% of them. And that's something that I deeply care about, but it's also, practically speaking, the only way to make the most of the science in the world of time domain, where things happen very, very fast. So you need as many people as possible to have a look at your data. So the reason why I told you that LSST is not necessarily a good game to play if you care about fast evolving transients like a kilonova is very well explained by the slide that you have in front of your eyes. So what you have there is a type 1a supernova. So it's a transient that is not slow. And you can see how well we would be able to sample this type 1a supernova if we were to use the wide deep fast cadence of LSST. So the data points that you see are the realization of this type 1a supernova within the LSST survey. And you do understand that if you do care about kilonovae that happen over a time scale of 1 week, and you want more than 1 or 2 data points, because otherwise you don't even know what you're looking at, this is really not the way to play the game. It's really not, LSST is not what you want. So instead, what we need to go beyond what we have done for 170817, which was so close by, is effectively to have a machine that is just like LSST, so with a deep view, so a big mirror. But it also needs to get on target very promptly. And that's why we started pushing for this target of opportunity capabilities on LSST. And what you have there is a plot where the only piece of information I would like you to bring home is that if you look at so you have some typical light curves of kilonovae at some reasonable distances where LIGO might identify gravitational wave source. And then you have as horizontal bars the threshold that different surveys can get to. And the surveys that we have right now, which is DECAM, ZTF, they just are not deep enough to sample the kilonova. Look at the 200 megaparsecs panels, and you will clearly see immediately that even ZTF will lose the counterpart, even the peak. So that's why LSST is the way to go about when it comes to discovering the kilonova. And there has been some reports in the literature that I find confusing, where one can play the game of asking the question, how about I just feel lucky and I just feel that LSST will cover my field of interest where the gravitational wave source is just by chance. Well, if you do numbers, this is actually not a great idea, because you will be left with a few percent probability to actually get the data that you care about. So think about having a beautiful gravitational wave source from a neutron star merger and have a few percent probability to even get on the target. It's definitely not a good way of playing the game. And that's why we started working on targeted opportunities on LSST and LS4. So now I switch a little bit gears and I get closer to the non-thermal part of the game. So the kilonova is that quasi-spherical component that dominated at early times. And now instead we are looking at the radiation that is coming from the jet, that very collimated outflow that is propagating into the environment, is shocking the environment, accelerating particles, and emitting through synchrotron radiation. And here, what you have are light curves of the afterglow, which is how we call the radiation coming from the jet interaction with the medium. And I picked an X-ray frequency in blue, an optical frequency in purple, and then 2 radio frequencies in red and orange. Overlaid, you have different jet models, and you can see like the dashed line, solid lines, and dotted line, and you can see right away, even before I tell you what all of this means, but you can see that there are multiple jet models that can actually go through reasonably well through the data. And if we look at the spectrum, so now I'm looking at the same components, but I'm looking at the spectrum. I'm looking at a very broad SED that goes from the radio all the way to the X-rays. And I'm taking a slice at different epochs in time that you have named and circled for the first and the last one. So you can clearly see that during the first couple of weeks, we have radio and X-rays on the same power law, and then we have that excess in the optical that is actually due to the kilonova. But starting at 100 days, you can see that everything becomes consistent with our simple power law in the sky. Is the most well-behaved simple power law I ever dealt with, and the slope of this simple power law is absolutely well determined because we have the dynamical range of the frequency on the y-axis, on the x-axis of a factor 10 to the 8. So this is good and bad. So we're dealing with a simple power law spectrum, and that remained the same for 1,000 days when it comes to the non-thermal part. And let's just first talk about the great thing about it, and then I tell you what is the not as beautiful, not as exciting part of having just a simple power law. So the beautiful thing is that this is the first time we can actually measure this slope so well. And since the slope of the synchrotron spectrum maps to the slope of the particles, the relativistic electrons that have been accelerated, this means that for the first time, we can actually say with very high confidence what was the distribution of relativistic electrons behind the synchrotron spectrum. And we can use the particle acceleration theory to then understand that this shock, these accelerating particles, had a Lorentz factor between 3 and 10. And this statement is independent from anything, any model of the jet. Is just particle acceleration, and that's it. So that's beautiful because I believe we have a new window where we might be able to study particle acceleration using sources in our universe. The bad thing, here comes the bad thing, is that being a simple power law spectrum, that means that I don't have constraints, model constraints. So for those of you that deal with synchrotron, it means that the break frequencies are outside my energy range, and there is no way I can use them to constrain the model parameters. So this is ultimately the reason why we have so many lines, so many jet lines that can actually go through those data. So the reason why we have many different jet models, and the jet models are defined depending on how the energy is distributed inside the jet, within the jet angle. So the reason why we have many of these jet models that are able to go through the data is because of that simple power law spectrum that remained the same for 1,000 days. So that's the bad part of the thing. So just to spell out, so when it comes to modeling, these are we have a number of unknowns, and for now I don't even care too much that we know exactly what all of those variables are. But the meaning is that we have 1, 2, 3, 4, 5, 6, 7, 8 variables. And let's see how many constraints do I have. We have one constraint is that in the gamma ray burst literature, we always assume that we accelerate all the electrons into a parallel. And so we always assume that we accelerate all the electrons in our environment and that all the electrons produce synchrotron. If you are horrified by that assumption, you are very right to be so, but that's what is hidden under all the GRB modeling. Then we can constrain the spectrum, which gives us the slope of that relativistic electrons. We can constrain the rise time of the light curve. We can constrain where the light curve peaks, and we can constrain the peak of that light curve. So we have 4 constraints, and unfortunately, the decay doesn't add anything else. So we're dealing with a model that is under constraint. So that's the punchline. So all the jet afterglow models are under constraint by definition. And we have one more constraint that came from the fact that we could actually take a picture of this blast wave and actually see where the centroid was at radio frequencies. But again, we are still far from having all the constraints that we would need to solve the system. This is why for some quantities, and here I'm emphasizing the total energy, kinetic energy in the jet versus density, we do know their ratio very well. We do not know these two parameters independently because of the intrinsic degeneracy of our model. So if we compare 17/17 in the jet to the short gamma ray burst jets, there is definitely a part of parameter space that the two share. That's definitely true, but I can't put a single dot for 17/17 because the model is intrinsically degenerate. So what we could measure though is how off-axis we wear compared to the jet. So 17/17, the reason why, let me go back here. So the reason why the light curve starts to rise for a while is because initially the jet is not pointing at us and we're suffering from heavy relativistic beaming of the radiation. Then the jet starts to slow down. So the Lorentz factor of the jet becomes smaller, which means that the relativistic beaming becomes less severe. So the jet, the cone of radiation opens up. And at some point, it does intersect our line of sight. And when it does so, we reach the peak. So the rise time actually gives us information about how much off-axis we wear. And that information, together with the picture, the radio picture that I said we were able to take, allows us to understand how collimated the jet was in 17/17. And if you do those numbers, you will understand that the jet in 17/17 was a few degrees wide. And that piece of information is interesting because it allows us effectively to do a number of cross checks in terms of rates of events like 17/17. The idea behind being that if you have a jet that is a few degrees wide, and if we only detect these events at cosmological distances when the jet is pointing at us, that means that we are missing a lot of these jets that are not pointing at us. And that's why there's a piece of inference about the jet opening angle of 17/17 is actually very, very, very important. It allows us to reason about rates, and answer questions like, is the short GRB rate consistent with the neutron star merger rate from GWs? The answer is yes. And the estimate that you see on this plot has actually been refined by the most recent LIGO publications. It went down a little bit. And is the rate of 17/17 like events consistent with the short GRB rate? The answer is yes. Is that consistent with the neutron star merger rate? And the answer is still is again yes. So the punchline is a 170817 is very likely to be just like a short gamma ray burst, but seen off axis. And as of now, it's very possible that all GW sources, all neutron star mergers produce a short gamma ray burst. It's still allowed, statistically speaking. So let me now do fast forward to the present epoch. So if everything was just a jet that came, whose radiation came into our line of sight after a while, all we should be observing right now, it should be just this decay. This yellow line should just keep going down for a long while. And this is the hypothesis, the H0 hypothesis that we went in when we kept getting observations of 170817. And the surprise is that if you look at the image, you have an X-ray image on the left and a radio image on the right. And you have NGC 4993 is a host galaxy of 170817. You can clearly see that, yes, the host galaxy is still there, thankfully. And you can clearly see that while we did not detect at a plus tau at 1200 days any radio emission, we did detect photons, X-ray photons from 170817. We're talking about 10 photons, but those photons should not be there. So they're telling us something special about this event. So let's zoom into the X-ray evolution of this transient and just focus on the prediction of the jet afterglow models, which are in dark blue. And then you can see how the latest data points are in light blue. They start showing some excess compared to the predictions. And I want to be clear, we're not talking about a 9 sigma, 10 sigma excess, not at all. The evidence for an excess is at the level of 3.5 to 4 sigma. So there is still possibility, some possibility that this is a statistical fluctuation with, but the possibility is with that significance. So there is still non-zero, but it's still interesting that we have a 3.5 to 4 sigma excess. So, okay, that's not important. So there has been a lot of confusion in the literature, and I just want to spend just one slide in case you're familiar with this literature and you heard different statements about the presence or lack of this excess. And a lot of the confusion has to do with the fact that we are really talking about, I think, 11 photons. So we are talking about a process that is highly Poissonian. Not only the source is highly Poissonian, but of course the detector noise that for Chandra is very low is also completely Poissonian. So the only way to understand the statistical significance is by allowing the source to be Poissonian as it should, and then we should totally avoid using instrumental responses. We should use whatever the instrument was doing right at that time, again, because we're dealing with literally very, very tiny signals, so we need to be as careful as possible. And here I'm just listing all the mistakes that, in my opinion, have been made in the literature. So yeah, so okay, I was wrong. Not only that we have 8 photons in the first observation and 16 in the following observation. The punchline is that we are really at the limit of what the most sensitive X-ray spacecraft that we have right now, which is Chandra for the source, can do. So unless the source rebrightens with time, this is going to be probably at the last observations with Chandra, and we would have to wait for the next generation of spacecraft to actually see what happens afterwards. So here is just one slide about the statistical significance, but I want to jump to the reason why if this excess is confirmed by future observations, why this is so potentially exciting. And the reason is because of what physics might be behind this axis, which might be related to two areas. So that I will just use a few minutes to chat about. One has to do with the kilonova afterglow, and I'm going to define in a second what that is. And the second possibility is that we are seeing accretion coming from the newly formed black hole. So when we have a neutron star merger, we have produced some new object. And at early times, let's assume that at early times, this object, the central object, whatever that was producing X-rays. Even in that case, at early times, we have so much ejecta, kilonova ejecta around, those X-rays would not have been able to get out. They would just die and get thermalized in the ejecta. However, at late times, like right now, we might be able to see some of these X-rays that survive the interaction with the ejecta, and they might get to us. So that's the accretion interpretation, if you want. And let me just say a couple of words about the kilonova afterglow shock possibility. So we have talked about the kilonova with that red and blue part, and we have talked about that in the context of optical emission. But just like any outflow that is launched in space, it will likely have a distribution of velocities. And the optical light is tracing the slowest part of this outflow. And it's not telling us anything about the fastest portion of the kilonova outflow. And the idea here is that the fastest part of the kilonova ejecta is driving a shock in the environment. This is happening for sure. And that shock, just like any other shock, accelerates particles and produces singletron radiation. So it's possible that what we are seeing is the emergence of the kilonova afterglow right now. And the reason why it took so long for the kilonova afterglow to emerge is because while in the jet, we are dealing with something like maybe 10 to the minus 6 solar masses of stuff, so it's extremely light. So deceleration happens very fast. The kilonova ejecta is heavy, so it takes time to decelerate, and you have the peak of radiation on the deceleration time scale. So you need to wait for time for that ejecta to transfer its kinetic energy to the environment. But the reason why that is so exciting is because if we put the information that we have on this plane of kinetic energy versus specific momentum, so let's think about that as a velocity. So we do know very well the information about this low part of the kilonova, which is that puffy purple dot. But what we do not know is how stratified in velocity was the ejecta of the kilonova. That we don't know. And that stratification has a connection to the nature of the remnant object that was formed. So the reason why I'm potentially so excited about, I'm so excited for the potential axis is because by modeling that axis of radiation, we might be able eventually to select what alpha parameter is the right one. So how was, in other words, we might be able to understand how was the kilonova ejecta stratified in velocity. How was the kinetic energy divided up in velocity space for the kilonova? Which is something that simulations predict as a function of the remnant object. And I believe I'm almost running out of time, so I'm gonna go a little fast. And I just want to touch upon in 30 seconds about the other option, which was the accretion that I told you early times. There's no way these X-rays can get out, but at late times of 1,000 days, you do your numbers with opacities and such, and you will find out that yes, these X-rays can actually get out. And it will be exciting if what we were looking at in the X-rays, which has a very particular So the luminosity of these X-rays is something 10 to the 38, and I'm sure that each of us, as soon as we hear 10 to the 38, we just go to L. Eddington by nature. So it would be very exciting if what we were looking at is the emergence of radiation from some accretion that is happening on the black hole remnant. So no matter what is happening in the future, and we will find out with new observations that will happen, no matter what is the correct explanation, it might be very exciting because we might be able to understand more of the nature of the new object that was formed, which is one of the big open question marks in 1717. And I'm happy to take any question that you have.
Okay, great. Yeah, thank you, Raffaella, for that really interesting talk. I hope you'll all join me in a physical or digital round of applause. So it occurs to me that I'm a little bit behind on some questions that were dropped in the chat. So let me attend to those really quickly. So Susan has asked, what of ongoing monitoring for 170817? This was discussed a little bit, but perhaps Susan, you wanted to follow up?
Yeah,
I thought it was discussed extensively, but thank you very much.
Yeah, is that we're doing both Chandra. So it's Chandra monitoring. Chandra is the only X-ray spacecraft that can see this level of X-rays, and then we're doing VLA, very, very long exposures, where 40 hours of VLA time that is about to be acquired on this source. So right now it's not detected in the radio anymore, but we're going as deep as we can.
Okay, thank you.
And I also see there was a question in the chat from David Brin. The equatorial kilonova is largely heavier nuclei who have momentum to escape from the magnetic fields that channel light stuff towards the poles.
If I can explain, it seemed to me that the equatorial kilonova effect, your chart seemed to say that these were heavier nuclei who could not be trapped by the magnetic fields toward the poles, whereas the lighter stuff is trapped, ionized and trapped by the magnetic fields to head toward the poles. Is this the conclusion that this seems to suggest?
So yeah, so there are actually many sources of outflows. So many different physics behind different types of ejecta, even in the kilonova. So there is a dynamical, for example, there is dynamical ejecta that is literally, it is what the name sounds like. It's like ejecta that is lost on mostly on the equator. There is also what you're talking about on the pulse is the jet, I believe, jet plus cocoon. I think you're muted, but
the red one is polar, and one assumes that feeds into the jet.
So the red one, so the red kilonova is mostly equatorial.
Oh, sorry.
The blue kilonova, the blue kilonova is actually mostly on the poles, but that ejecta component is independent from the jet to some extent. So the jet, it's good to think about the outflows as separated. And you're right that there might be B field that is driving the jet launching. I don't think that the community agrees on how to launch a jet in this for neutron star mergers, not at all.
Okay, if in the absence of follow-up on that point, it looks like Jim Latimer has his hand raised.
Yes, if you could go back to the slide that showed the, forget which number it was, the rate of mergers.
Yeah, that's the slide that has to be updated, by the way.
You had a horizontal and vertical lines, and I'm confused by that figure. If you can explain it again.
Yeah. So that's
Yes.
This one, right? Yeah.
Yes.
So here, what I was trying to understand was if so one of the questions that we had was, is it possible that all neutron star mergers with a rate as based on what LIGO is telling us, is it possible that all neutron star mergers produce short gamma bursts or not? So you have the neutron star merger rate from GWs, which is this orange shaded region, And then you have the short GRB rates from different people that compile them with this diagonal bands. And you can see that there is a region of overlap depending on how much beamed the short GRBs are. So that's one part of the figure. And then we can ask the question, okay, and then we can put the theta jet of 170817 that in my opinion is interesting that it does overlap where the other two regions are also overlapping. And then we can also play a different game of saying, we received some signal in the gamma rays from 170817. And that we know that is not the core of the jet, is most likely some wider angle component. And we can ask the question of observationally, what's the rate of 170817 like events? So meaning what's the rates of these wider angle outflows? And you can see that again, there is a region of overlap between this rate in red and the neutron-star merger rate, provided that these wider angle outflows are at least 10 degrees or larger. So the bottom line is that it's possible, and again the LIGO rate went down, so it would be like shifted. The orange band should go down a little bit. So the conclusion is that right now it's possible that all neutron-star mergers that LIGO sees are short GRBs, and that it's possible that each of them have a cocoon component, just like 170817 had.
Okay, great. Can you tell me what the revised rate is? Does it go between 200 and 1,000 now, or what?
I'm forgetting now the right number, but I think it's can you see my cursor? I think it's like 800 or so, 800 and maybe a couple of hundred. I actually had the updated plot somewhere I can share.
Okay, great. Thank you.
Mm-hmm.
Okay, and the next question goes to Ellen. You are muted.
Hi, Raffaella. That was a great talk. Could you put that slide back that you were just showing? So not to drag the conversation too much again in this direction, could you say something about what the upper and lower limits on the merger rate are defined by? Of this orange band. Yeah,
the orange band is all LIGO. So
right.
Yeah. So it's based on their sensitivity, calculation of their sensitivities, the amount of time they were in the sky, and the number of events that they detected, and that is where that number comes from. The range comes from.
So what about how certain is the population modeling? I mean, to what extent do you think we know the neutron-star merger rate in the universe?
Oh, like going from the stellar, like a binary. Yeah. So okay. So I think we are doing much better than what we were doing 20 years ago when there was many orders of mag uncertainty. But all of those stellar population synthesis models, and I'm not an expert there, so I'm talking as an outsider. They have many knobs to turn. So in my opinion, the most promising way is actually to invert the line of inference and use, now that we can detect neutron-star mergers with GWs and hopefully more EM counterparts, to invert the line of inference and go from our observations to actually inform their simulations instead of vice versa.
Okay, so we're a minute and a half after 1 o'clock. So if people have to leave, then of course, please feel free to do so. But we're going to continue with the questions anyway. And the next question looks like it goes to George.
Thank you, Raffaella, for a great talk. That was a very intriguing look at the future of time domain astronomy. You mentioned something about using Chandra to look at the X-rays from, I guess, short duration gamma ray bursts. And I have two questions about that. So one is, it looked to me from your curve, I thought I saw that the X-ray emission is actually fairly peaked in time. It's actually not, it is a transient.
Yeah,
Or
yeah.
at least it falls off, and then it's kind of steady for quite a while as you get presumably accretion on a black hole, right? But it looked to me like it was peaked early on, and the luminosity was pretty high.
Yeah, well, high. It is high, but the sources tend to be very far, so at the end it's very faint.
Well,
But
that's
you're
okay.
right.
So
Yeah.
so then you were mentioning Chandra, but we have presumably in the a number of us are interested in the next generation of X-ray telescopes like Prism and Athena that would have very high energy resolution of order a few electron volts. So I'm just wondering whether that opens up any issues here.
Yes, so Athena, wonderful. Yes, I just gave a talk to the Athena community too. So with Athena, if Athena goes well and is launched and everything goes well, you could be monitoring the source for 30 years more. So flux-wise, it's great. So in terms of energy resolution, so all we've seen until now is synchrotron. So in that case, the energy resolution doesn't buy you anything because we don't have lines. But if now we have accretion maybe emerging, that maybe might give us some more less boring spectrum to look at.
Very good, thank you.
Okay, and it looks like the next question goes to Sanjay.
Hi there, thanks for a nice talk. I have maybe a naive question about objects after the merger. If the object that's left behind is a neutron star, a very massive neutron star, which is expected to be magnetized, it might behave like magnetars do when they are early in their life. And giant flares, for example, could be one potential signature of a massive magnetized neutron star. So my question is, what observing opportunities would a giant flare give you? And are there any challenges that we have to overcome before we can start detecting giant flare-like phenomena from mergers, post-merger?
Yeah, so actually what you're saying is something that people have been trying to look for any sort of variability of these X-rays that we are detecting with Chandra, and there has been a claim of some variable phenomenon around the peak that I investigated personally, and my conclusion is that it's not significant. So in my opinion, after you account for the Poissonian nature of the process, there is no evidence for any significant variability. It's very true that we are photon number limited, so the variability that we can investigate is limited by how many photons on the detector we get. But yeah, I mean, that's definitely very true. If there is a surviving neutron star, maybe we have the possibility of having flares. I have to say that another manifestation of that would be that we would also have an energy reservoir from the magnetar, like from the spin down. And I would say that based on the colors of the kilonova that we've seen for 17 based on the energetics of that kilonova, I would find it unlikely that we had a surviving neutron star, surviving until now. But yeah, it's definitely something that we should keep an eye on for the next events.
So just to follow up on that, do we have the instruments that can detect a giant flare-like phenomena?
Giant flares, they get to what luminosity? They don't. Oh, sorry, that's my family. I think that the giant flares are actually out of our reach in terms of luminosities.
Okay. Okay.
That's but it's also true that I don't think we've ever seen a neutron star right after birth. So maybe they do even more giant flares.
Okay.
So as an observer, I would keep my eyes open and look for them.
Okay, thank you.
Okay, and I see Jim's hand again.
Yeah, if I can, I had a second comment. On an early slide, you had indicated that the compact remnant of supernova 1987A is not really identified yet. But I would point out that there's now evidence that there's a dust blob that has the right luminosity if it's if buried within it is a 35 or 40-year-old neutron star.
Yeah,
So
yeah,
I just
yeah.
wanted to point that out, that there, in all likelihood, I think the remnant is identified now. So
Awesome. Yeah, yeah. I've been reading about it, and I know that not all the community would agree, but I would be very excited if that is the explanation. Yeah, I agree
yeah,
with you.
okay, good. All right, thank you.
All right, and it looks like Dake has a question. So
Well, yeah, I have maybe two naive questions. So first, you mentioned this sort of delayed acceleration scheme that explains the rise in some flux later, like hundreds or even thousands days after the merger. So given we have some understanding of the model and also this observation, would it be possible to use such variation to find maybe other mergers like happened earlier without gravitational wave counterparts?
Yeah, so tell me if I got it right. So you're saying if we're seeing now this new component emerging, maybe there has been other events for which this is happening, and we can find this later component that is rising right now. Is that what you're saying?
Yeah.
Awesome. Yeah. So yes, what you're saying is very, very, very correct and true. And we did try to go after short gamma ray bursts at late times. We did that with the very deep radio observations, and we found nothing. The problem is that, again, this is at the threshold of what we can do at 40 megaparsecs right now. And all the other short GRBs are at least a factor 10 more distant. And so factor 10 more distance is a factor 100 in flux. So it's beyond our capabilities, but your idea is a great one.
Okay. And I think you briefly mentioned that there are some maybe optical signatures for pre-supernova stars. So can you maybe say a bit more about this? So what observations specifically that we have, and do we expect all stars to have those behavior?
Yeah, this is part of something that I couldn't even touch upon today. So thank you for the question. So it's becoming clearer and clearer that every single time we have the depth and sensitivity to look for outbursts before supernovae, we tend to find them. So the statement that I can say right now is that most likely most massive stars, they do experience outbursts before death in the final moments. And we were able to find one, like it was just a couple of months ago that the paper came out, where we found an outburst from the most common type of supernova ever seen. So that means that most likely all massive stars do it. And we are just, until now we were missing the sensitivity to see those outbursts. There's a lot of beautiful physics about the instabilities during the last nuclear burning stages of massive stars that we're probably not understanding, and it's a beautiful place for investigations in the future.
Okay, thanks a lot.
okay, do we have any more questions, or perhaps I can stop the recording and people can ask their question when it's not going to be on wax. Yeah, okay. Perhaps let's thank Raffaella again for a very lovely talk. Digital applause, physical applause if you'd like, and I'll stop the recording.
Okay.